Hello and welcome to my science tutorials. In today's video, we want to look at resonance frequency and Q factor or voltage magnification. Before we begin, if you're new to my science tutorials, kindly consider subscribing and turning on the notification button so that you do not miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So without further ado, let's begin. Now, in our previous tutorial, we made mention of the fact that in an RLC series circuit, where we have a resistor, inductor, and a capacitor, if we have our inductive reactance being equal to our capacitive reactance, we establish the fact that at this condition, we say that the circuit is at resonance. And the frequency at which this resonance occurs, okay, is what we are calling the resonant frequency. Resonant frequency. And we establish the fact that the resonant frequency is given to us as 1 over 2 pi the root of LC. Now, if we have resonance in our RLC series circuit and the resistance, okay, or the resistance is small, so the resistance of the resistor is smaller than the inductive reactance or the capacitive reactance. If this is smaller than both XL and XC, another special condition occurs. That special condition, it is possible for us to have our inductive voltage, our VL, which we are calling the inductive voltage, and then our capacitive voltage, capacitive voltage. Now, when we have the resonance and then our resistance is smaller than the inductive reactance and the capacitive reactance, we can observe that our inductive voltage and our capacitive voltage will be greater than the supply voltage. Okay, and when this occurs, we see that there is a voltage magnification, or there is something we call Q factor. This simply means that when we have an RLC series circuit, so we have a resistor, inductor, and a capacitor connected to an AC source, and then we have our inductive reactance to be equal to our capacitive reactance, and our resistance here is very small. Okay, we are expecting that the voltage over here, assuming this is 20 volts, if this is the voltage supply or the supply voltage, it is possible for the voltage across just the inductor to be greater than 20, so something like maybe 30, and this guy, the voltage across the capacitor can be something like 40. So if we see this, we can see that the voltage across the inductor VL is greater than the supply voltage, which is 20, and then the voltage across the capacitor is also greater than the supply voltage. Now, when this happens, we say that there is a voltage magnification or Q factor. So how do we calculate that voltage magnification or the Q factor? So the voltage magnification is given to us mathematically as the voltage across either the inductor or the capacitor on the voltage supplied or the supply voltage. So it is the voltage, that the ratio between the voltage across the inductor or the capacitor to the ratio of the voltage supply. Now, this ratio is a measure of the quality of the circuit, that is as a resonator or a turning device, and we call that the Q factor. Now let's look at some calculations or how we can derive an actual formula that we can use for our Q factor. Like I said, the Q factor is equal to our voltage magnification. So let's look at how to do or how to derive a formula for voltage magnification. Now we said that this occurs at resonance, and then at resonance we have a resonant frequency, and then we also established the fact that resonant frequency is equal to 1 over 2 pi the root of LC. So this is at resonant frequency. We also established the fact that Q factor or the voltage magnification is the ratio of inductive voltage on the supply voltage. Okay, so this is equal to our inductive voltage will be IXL over our voltage over here, supply voltage will be IR in this case. So since the current are the same, this is XL over R. We also said that Q factor can also be the voltage across the capacitor over the supply voltage. So this can also be IXC over IR, which is also equal to XC over R. Okay, so this is the formula for both, but if you like you can further break them down. So XL is 2 pi FL over R, and XC is, this guy is 1 over 2 pi FC over R, and this will give you 1 over 2 pi FCR. Now remember the frequency here is resonance frequency, so it's FR. Okay, now let's look at something that happens and how we can derive a simpler formula for resonant frequency, for Q factor. Okay, so from here over here, let's make this our equation 1, this our equation 2. So from here, let's try to do something. Let's cross multiply. So if you cross multiply, we're going to have resonant frequency multiplied by 2 pi to be equal to 1 over the root of LC. So this means that if we have 2 pi multiplied by frequency, it should be equal to the ratio 1 over the root of LC. So let's make this equation 3. Now let's take one of this formula. So let me take the first equation, which is equation 1. So taking equation 1, let's do some substitution. We say that Q factor is equal to 2 pi FRL over R. Okay, and we also established from equation 3, or using the resonant frequency, we realize that the 2 pi F here can be replaced by 1 over the root of LC. So let me rewrite that. This is 2 pi FR multiplied by L over R over here. And so in place of 2 pi FR over here, we can substitute this. So Q factor is equal to 1 over the root of LC multiplied by L on R. So this will be equal to L over the root of LC multiplied by resistance. Okay, so now let's break this guy down and see what we can have. So this is equal to, let me do it at the bottom here. So our Q factor will be equal to, let me factor out 1 over R. So I'm going to have 1 over R outside. Okay, then into bracket I will have L over the root of LC. Okay, this is still the same as what we have over here. So this is equal to 1 over R multiplied by L over the root of LC can be written as C raised to the power half L raised to the power half. Okay, because the root sign is power half. Okay, so if we do that, it means this is equal to 1 over R, then into bracket we have L at the top with the power 1, so we can bring this guy to the top. Okay, indices. So if you send this guy up, it will become negative, so minus half on C raised to the power half at the bottom over here. So this is equal to 1 over R into bracket, and we have L1 minus L raised to the power 1 minus half will give us L half on C also raised to the power half. And we know half is the root, so this finally is equal to 1 over R into brackets the root of L on C. The root is covering both because this is also raised to the power half, this is also raised to the power half. So at the end, we are saying that our Q factor can be given to us mathematically as 1 over R multiplied by the root of L and C. So this is the formula for our Q factor. Okay, so you can either use this formula for the Q factor, or you use the formula over here, equation 1, or you use the formula here for equation 2 if you have the resonance frequency and the other parameters. But this is a much simpler formula. So you can either use this formula over here, this formula over here, to find your resonant frequency and the Q factor. So let's go ahead and look at some examples to actually appreciate what we are doing. So example number 1, a coil of inductance 80 millihenry and negligible resistance is connected in series with a capacitance of 0.25 microfarad and a resistor of resistance 12.5 ohms across a 100 volt variable frequency supply. We are to determine I, the resonant frequency, II, the current at resonance, III, how many times greater than the supply voltage is the voltage across the reactance at resonance, or simply put, the Q factor. So this is very easy. Let's write down our solution. Alright, so let me use another color for the calculation. Right, so we're told that a coil of inductance, so we have our inductance L to be equal to 80 millihenry, and we also have our capacitance C is equal to 0.25 microfarad, and then the resistor of resistance 12.5 ohms, and then a voltage of 100 volts supply. The first thing we're asked to find is to find the resonant frequency, so FR. So resonant frequency, as we saw earlier on, is 1 over 2 pi the root of LC. So this is equal to 1 over 2 pi the root of the L, our inductance, is 80 times 10 raised to the power minus 3 multiplied by the capacitance 0.25 times 10 raised to the power negative 6. Okay, so if we compute everything we have here into our calculator, our resonance frequency is equal to 1.125 kilohertz. So this is what we are going to get as our resonant frequency. So II, the current at resonance. To find the current at resonance, we establish the fact that V is equal to IR when we have a resonance in an RLC series circuit, so we don't need to find Z, which is the impedance. So from here, we can make current the subject. So if we make current the subject, we have voltage on resistance, and this is equal to our voltage supply is 100 over here, and then our resistance over here is 12.5 ohms. So 100 divided by 12.5 is going to give us 8 amperes as our current. So let's look at III. How many times greater than the supply voltage is the voltage across the reactance, or the reactance at resonance? So there are so many ways that we can find this, so we are going to be finding it one after the other. So the first one we can do is, this is Q factor. The first way is to use the formula direct, so 1 over R the root of LC. So this is equal to 1 over the resistance is 12.5 multiplied by the root of our L is 80 times 10 raised to the power minus 3 over our C is 0.25 times 10 raised to the power minus 6. So this is equal to, if we multiply everything we have over here, we are going to get 45 0.25 volts as our Q factor. Now, another way we can go ahead and solve this is when we use the normal definition of the Q factor. So let me get some space and let's look at that. So another way to find our Q factor is equal to, we said that Q factor is the ratio of VL, the inductive voltage, over the supply voltage, and we also saw that that can be equal to IXL over IR, and that is equal to XL over R. And we said that our XL is 2 pi resonant frequency L over resistance. So this is equal to 2 pi. The resonant frequency, as we've calculated, is 1.125 times 10 raised to the power 3. Then multiplied by our L is 80 times 10 raised to the power minus 3. All on the resistance over here, 12.5. So it's 12.5 ohms. Then if we compute 2 pi multiplied by the frequency multiplied by this divided by 12.5, we are going to get our answer to be 45.24 volts, which is actually also the same as the first answer we got over here. Or we can also say Q factor is equal to VC over V, and that is equal to, we saw that earlier on, that if we do that, we are going to have 1 over 2 pi resonant frequency CR, and if we do that, 1 over 2 pi multiplied by resonant frequency, which is 1.125 times 10 to the power 3, multiplied by our capacitance, in this case is 0.25 times 10 to the power minus 6, multiplied by the resistance, which is 12.5, we are going to still get the same answer, 45.24 volts over here. So we realize that for calculating resonant frequency, whether you use the voltage VL over V, or you're able to break it down to 2 pi FR L on R, or you use VC over V, or you use the general formula, the inverse of resistance multiplied by the root of LC, you are still going to get the same answer for Q factor. So there are so many ways to calculate Q factor. You just have to select the one that is best for you, or the easiest way that you can identify. So let's have a look at another question. So we have a series circuit comprises of a coil of resistance 2 ohms, an inductance of 60 millihenry, and a 30 microfarad capacitor. We have to determine the Q factor of the circuit at resonance. So this is also very easy. So let's go ahead and look at that. So let's write down our solution. So we have a series circuit comprising of a coil of resistance. So our resistance is 2 ohms. We have our inductance L is 60 millihenry. We have our capacitor having a capacitance of 30 microfarad. So we have to determine the Q factor. Now, like I said, there are so many ways to find Q factor. So let's go with the obvious one. So the easiest one is for us to say Q factor is equal to 1 over R multiplied by the root of LC, and this is equal to 1 over 2 multiplied by the root of L is 60 times 10 raised to the power minus 3 on 30 times 10 raised to the power minus 6. So if you do that, we are going to get 22.36 volts as our Q factor. Or we can find the resonant frequency first. So resonant frequency FR is equal to 1 over 2 pi, the root of LC. So if we do that, we have 1 over 2 pi, the root of our L is 60 times 10 raised to the power minus 3, multiplied by our C is 30 times 10 raised to the power minus 6. Then if we compute everything there, it's going to give us a resonance frequency of 118.63 hertz. Now using this resonance frequency now, we can calculate our Q factor by saying our Q factor is equal to XL over R. And then we know that XL is 2 pi resonance frequency L over R. So this is equal to 2 pi multiplied by the resonance frequency 118.63 multiplied by our L, which is 60 times 10 raised to the power minus 3, all divided by the resistance, which is 2. And if we do that and we do the computation, we are going to get 22.36 volts as our answer. Or we can say Q factor again is equal to XC over R, which is equal to 1 over 2 pi resonance frequency RC, and this is equal to 1 on 2 pi multiplied by 118.63, which is the resonance frequency, multiplied by our resistance, which is 2, multiplied by our capacitance, which is 30 times 10 raised to the power minus 6. So if we do that computation again, we're also going to get 22.36 volts. So there are 3 different ways to calculate the resonance frequency. The Q factor. You can use the formula straight ahead to get your answer, or you can find your resonance frequency and use it in this formula, XL over R or XC over R, to also get your resonance frequency. So let's look at one more example. We have a coil of negligible resistance and inductance 100 millihenry is connected in series with a capacitance of 2 microfarad and a resistance of 10 ohms across a 50 volt variable frequency supply. We are to determine the resonance frequency, the current at resonance, the voltage across the coil, and the capacitor at resonance, and then the Q factor of the circuit. So let's go ahead and look at this. So let's write down our solution. So let's list our parameters. We have an inductance of 100 millihenry. We have a capacitance of 2 microfarad. We have a resistance of 10 ohms. We have a voltage supply of 50 volts. And we're asked to first of all find the resonance frequency. So let's do that. Resonance frequency FR is equal to 1 over 2 pi, the root of LC. So this is equal to 1 over 2 pi, the root of our L is 100 times 10 raised to the power minus 3, multiplied by the C is 2 times 10 raised to the power minus 6. Then if we compute everything we have over here, we are going to get the resonance frequency of 355.88 hertz. Okay, so now that we have the resonance frequency, let's look at II. We have to determine the current at resonance. So the current at resonance is equal to voltage on resistance, and that is equal to our voltage is 50, our resistance is 10, so this is equal to 5 amperes. So let's go ahead and find the third one, III, the voltage across the coil and the capacitance at resonance. Okay, so we're told that the coil has a negligible resistance and then inductance. So because it has negligible resistance and only inductance, it means our voltage across that V coil is equal to IXL, and that is equal to, the current is 5, and then we know that XL is 2 pi resonance frequency L, and that is equal to 5 multiplied by 2 pi. Okay, let me make this bigger. Our resonance frequency over here, we said, is 355.88 multiplied by L, which is 100 times 10 raised to the power minus 3. Okay, so this will be equal to 5 multiplied by the 2 pi multiplied by the resonance frequency multiplied by L, will give us 223.61. Then if we multiply that by 5, we are going to get 1108.03 volts. So it's 1118.03 volts as our V core. And then we can go ahead and find the voltage across the capacitor VC. VC is equal to IXC, and this is equal to I. XC is, this is I current multiplied by XC is 1 over 2 pi FRC. So this is equal to 5 multiplied by 1 on 2 pi multiplied by the resonance frequency 355.88 multiplied by the capacitance, which is 2 times 10 to the power negative 6. Okay, so if we multiply everything we have over here, we're going to get 1118.04 volts. Okay, so we have our V coil, we have our VC over here. So that is the voltage across the coil and the resistance. So let's look at IV, our Q factor. So the Q factor, we can use, we know that Q factor is equal to either VC or VL over V. So this is very easy. We can just use 1118.04 on the voltage supply, which is 50, and then that is going to give us 22.36. Or if you like, you can use Q factor is equal to 1 over R, the root of L on T, and you realize that you are still going to get the same answer, 22.36 volts as your answer for Q factor. So thank you so much for watching, and then I will see you in the next video. Bye bye.